Hey you guys, this is Mr. Millings, and today I just want to go over 6 of the most missed problems from the Thermochemistry unit review that was on Moodle a couple days ago. So let's jump right in and take a look at some of these problems. Okay. Alright, in this first problem here, it says an engine releases 16 kilojoules of heat and does 14 kilojoules of work. We are asked to calculate the change in the internal energy of this system. We learned earlier this unit that to calculate the change in a system's internal energy, we have to know two things: the amount of heat, or Q, that the system is absorbing or releasing, and we have to know how much work the system is doing, or how much work the system is having done on it. If we know these two things, we can quite easily calculate the change in internal energy of a system. So in this problem here, it says that the engine is releasing 16 kilojoules of heat. Okay, so if it's releasing 16 kilojoules of heat, then the sign of heat will be negative. Okay, if the system is releasing heat, the sign will be negative. If the system is absorbing heat, the sign will be positive. Okay. Furthermore, if we read on, it says that the engine here, or the system, is doing 14 kilojoules of work. So the engine is doing 14 kilojoules of work on its surroundings. Alright, anytime the system is doing work on the surroundings, the sign of this will also be negative. Anytime the surroundings is doing work on the system, then work will be positive. So now that we know these two values, we just use this formula here and plug in our answers, or our values. So we got delta E is going to be negative 16. Let me erase this. Negative 16 kilojoules plus a negative 14 kilojoules of work. Alright, if I put this in my calculator, I will get a negative 30 kilojoules. So overall, this system is going to end up releasing 30 kilojoules of energy. Alright, so our final answer here will be negative 30. Let's look at the next one. Alright, in this problem here, it says how much thermal energy must 150 grams of ice at negative 20 degrees Celsius absorb in order to change it to water at 90 degrees Celsius. So anytime we have problems where we're asked to calculate how much thermal energy something is absorbing or releasing while there is a temperature or a change in state of matter, I like to draw a little picture first and see what's happening. So in this problem here, it says that we've got a 150 gram piece of ice, and it says that this 150 gram piece of ice is at negative 20 degrees Celsius. And what's going to end up happening to this ice over time is that it looks like it's going to change into water at 90 degrees Celsius. Its mass is going to stay unchanged. So we've got a piece of ice, and this ice is going to absorb a certain amount of thermal energy, or Q, and that's what we're trying to figure out. This ice is going to eventually melt at 0 degrees Celsius, which is the freezing point or melting point of ice. In this case, that will be the melting point of ice. And then it's going to continue to heat up to 90 degrees Celsius. Okay, so if we take a look at this right here, between negative 20 and 0, we've got ice, and between 0 and 90 we have water. So what we will first have to do in step 1 is calculate how much thermal energy the ice will absorb as it goes from negative 20 to 0. In step 2, because we have a melting point here, we will have to calculate the heat of fusion. And in step 3, what we will then have to do is calculate how much thermal energy this water is going to absorb as it goes from 0 to 90. Once we have these 3 steps answers, what we can do is add these 3 numbers up and get our final answer for the total amount of thermal energy this ice will need to absorb. Alright, so up here in step 1, let's figure out how much thermal energy the ice will absorb as it goes from negative 20 to 0. The way we do that is by using the thermal energy formula. Q equals C times M times delta T, where the specific heat of ice is right here. Specific heat of ice is 2.03 joules per grams degrees Celsius, times the mass of this ice, which is 150 grams, times the change in temperature as it goes from negative 20 to 0, which is a positive 20 degree temperature change. We'll get a calculator out here, and we end up with 6,090 joules. Okay, and this answer will be positive since the ice is absorbing thermal energy. So 6,090 joules will go here. In step 2, what we need to find is the heat of fusion. To get the heat of fusion, we take the mass of this substance, which is 150 grams, and we multiply it by the heat of fusion of water, which is 334 joules per gram. Once again, because the ice here is absorbing thermal energy, we will have a positive heat of fusion here. So take 150 times 334, and you will get 50,100. So we'll put that here. There we go. In step 3, we need to use Q equals Cm delta T to figure out how much thermal energy this water now is going to absorb as it goes from 0 to 90. So the specific heat of water is 4.18 joules per gram degree Celsius, times the mass, which is the same, 150 grams, times the change in temperature as it goes from 0 to 90, which is 90 degrees Celsius. Put this in our calculator, and we get 56,400, it looks like. 56,430 joules. Once again, this will be positive since the water is absorbing thermal energy. Alright, so now that we figured all these 3 steps out, I simply add them up. And it looks like I end up with 112,620. If I want to convert this to kilojoules, I simply slide this decimal over 3 times, and I get 112.6 approximately kilojoules. And last but not least, if I want to figure out how many calories this is, I simply take the joules and divide it by 4.18, and I will end up with my answer. Looks like it's about 26,942.6 calories. Alright, so how much thermal energy will this ice need to absorb as it goes from negative 20 to 90? It looks like it's going to need to absorb this many joules, this many kilojoules, or this many calories of thermal energy. Let's take a look at the next one. Alright, this one here is very similar to the problem that we just did, except in this one here, I'm basically asking you to show your work by plugging in your solution into these boxes. So once again, we have a thermal energy problem where we're asked to calculate how much thermal energy is either released or absorbed as this substance is changing state of matter. So I will draw a little picture. It looks like we've got 500 grams of water vapor. So I got 500 grams of water vapor, and this is at 175 degrees Celsius. And what's going to happen to this water vapor is that over time, it looks like it's going to release thermal energy. Alright, so this water vapor is going to release a certain amount of thermal energy that we're being asked to figure out. And as it releases thermal energy, it's going to cool down into a chunk of ice that is at negative 30 degrees Celsius. And the mass of this ice will stay the same. So as this water vapor cools down, it's going to condense at approximately 100 degrees Celsius. So it's going to condense at 100 degrees Celsius. So right here, here's the condensation point, right? So it's gas right here. It's going to be water from here all the way to 0 degrees Celsius, where this water will now freeze. At which point this water will turn into ice. Alright, so this is what a picture might look like that you will have to set up so that we can understand what's happening. In the first step, what we will have to do is figure out how much thermal energy this water vapor will release as it goes from 175 to 100. In the second step, we will have to calculate the heat of vaporization. In the third step, what we will have to calculate is the amount of thermal energy this water will release as it goes from 100 to 0. In the fourth step, what we'll have to calculate will be the heat of fusion. In the fifth step, what we will need to calculate is the amount of thermal energy this ice will now release as it goes from 0 to -30. Alright, so let's start with step 1 here. To figure out how much thermal energy the water vapor is going to release, all we need to do is use the thermal energy equation. Q equals the specific heat times the mass times the change in temperature. Alright, the specific heat of water vapor is right above here. It says it's 2.0 times the mass. The mass of this substance is 500 grams times the change in temperature as it goes from 175 to 100. Because it's cooling, that will be a -75 degrees Celsius. Get our calculator out. We take 2 times 500 times -75, and we'll get a -75,000 joules. Now we need to calculate the heat of vaporization. To get the heat of vaporization, we take the mass of this substance, which is 500 grams, times the heat of vaporization for water, which is 2,260 joules per gram. Where am I getting this number from? This is a number you will have to memorize. This will be negative since the substance is cooling down. And we get 1,113,000. And this is going to be negative. Try to get rid of this here. There we go. Alright, next we got to figure out how much thermal energy the water is going to release as it goes from 100 to 0. So the way we do that is by using this formula right here. The specific heat of water is 4.18 joules per gram degree Celsius. The mass of the water is still 500 grams, and the change in temperature as it goes from 100 to 0 is a -100 degrees Celsius. So I take 4.18 times 500 times a -100, and I get 209,000, -209,000. Now I need to figure out the heat of fusion. That's the amount of thermal energy it's going to take to freeze this ice, or to freeze this water. So the way I do that is by taking the mass, which is 500 grams, times the heat of fusion for water, which is 334 joules per gram. Another number that you're going to have to memorize. And this will be negative because we're going from water to ice. And I get -167,000. Last, I need to figure out how much thermal energy this ice is going to release as it goes from 0 to -30. So now I need to use the specific heat of ice, which is right here, 2.03. times the mass of this substance, which is 500 grams, times the change in temperature as it goes from 0 to -30. It's cooling down, so it'll be -30 degrees. So I take 2.03 times 500 times a -30, and I end up with -30,450. So now that I have these 5 values, what I simply need to do is add these up. So let me do that. Plus 1,113,000 a negative 1,113,000 plus a negative 209,000 plus a negative 167,000 plus a negative 30,450. And it looks like I end up with a negative 1,611,450 joules. To convert this into kilojoules, I slide the decimal over 3 times, and I will end up with 3 times to the left, that is, negative 1611.5 kilojoules. And to convert this to calories, I take the joules and divide it by 4.18, and I end up with 385,000. 514.4. Don't forget your negative, and there you go. So how much thermal energy must this water vapor release in order to convert it all the way to ice at negative 30 degrees? And it needs to release this much, this many joules, this many kilojoules, or this many calories. Let's take a look at the next one. All right, in this problem here, it's asking you to determine what the graph here is depicting. Well, if we take a look in this problem here, we have some reactants over here and we have some products over here. The reactants here have less energy than the products. So what must be happening here is that these reactants here are going to absorb energy. If the reactants absorb energy, then the products will end up with more energy, which is what we see right here. And anytime you have the system, in this case the reactants absorbing energy, this will be endothermic. So this is an endothermic reaction. However, what does that mean? There's 2 different endothermics here. Okay, endothermic, which means that the reactants are absorbing energy from their surroundings. So let's take a look here. Alright, so it looks like it's going to be this one right here. Endothermic, which means that energy is absorbed by the reactants. Let's take a look at the next one. In this problem right here, it asks you to determine what kind of process or chemical reaction is taking place. And once again, we have some sort of reactants over here on this side, and we have some products here. If you'll notice, the products have lower energy than the reactants. Well, how does that happen? Well, the reactants must release energy, right? It must release energy. Energy here is being released. Therefore, this is an exothermic process or exothermic chemical reaction. Let's take a look. Exothermic, which means that energy is released by the reactants. That looks good. Alright, let's take a look at the last problem. Alright, in this problem here, it says you have a 250 gram sample of gold. So you have some gold here. Right? And it has a mass of 250 grams. This gold is currently at 25 degrees Celsius. And what's going to end up happening is that this gold here is going to absorb 5,400 joules of thermal energy. And we're asked to calculate the final temperature of this gold if it absorbs 5,400 joules of thermal energy. We know the initial temperature is 25 degrees Celsius. So if we calculate for the change in temperature, or if we solve for delta T, and then add that to the final temperature, add that to the starting temperature here, we can then end up with the final temperature. Alright, so in this problem here, basically we're going to use the Q equals Cm delta T formula, and we will have to solve for delta T first. We know that delta T, by moving these variables around, is equal to Q over C times M. Alright, so let's plug these numbers in here. The change in temperature is going to be equal to Q, which is 5,400 joules, divided by the specific heat of gold, which is 0.13, times the mass of the gold, which is 250 grams. Now, when we put this in our calculator, make sure you put everything on the bottom or the denominator in parentheses. That will make sure that your answer is right every single time. So I'll take 5400 divided by parentheses 0.13 times 250. I'll close the parentheses and then hit equals. And it looks like the temperature change is about 166.2 degrees. Alright, so this is not our final answer. This is just the change in temperature. Alright, what we're being asked to find here is the final temperature. So, to get the final temperature, what I have to do is take the initial temperature and add the change in temperature. If I do that, I will get my answer. Alright, let me just fix this real quick. Okay, so in this problem here, the initial temperature is 25 degrees Celsius, and it looks like the change in temperature is 166.2 degrees Celsius. I'll get my calculator out here. It looks like I'm going to end up with 191.2 degrees. So going back to the question, if this 250 gram chunk of gold that's at 25 degrees Celsius absorbs this much thermal energy, what will its final temperature be? It looks like it's going to be 191.2 degrees Celsius. Alright, so I hope this was helpful. This was these were the 6 most missed questions from the review. Study up, and I hope this was helpful.